Hi, in this video I'll talk about the working principle of a DC motor. This is part A of the video. The basic input to a DC motor is a magnetic field shown here by a north and a south pole, and a magnetic field that's pointing from the north pole towards the south pole. You need a DC battery to supply current to a conductor, and the conductor must be placed inside the magnetic field. The output of a DC motor is rotation. So convert electrical energy into mechanical energy. The parts of a DC motor are shown here. The positive terminal of the DC battery is connected by a wire to a component which looks like a brush. Let's call it the positive brush, like a toothbrush. The brush connects the positive charges to a commutator. Let's call it commutator A, which is pink in color here. There's a green conductor that's connected rigidly to the commutator A. So the current will flow through the green looking conductor and come all the way back to the right hand segment of that green conductor. The green conductor's right hand segment is connected to the orange colored commutator. We call it commutator B, which is in turn connected to the brush, the negative brush as we call it. And then the current comes right back through the blue wire to the negative of the battery. In this way, the circuit is completed. Battery, brush, commutator, conductor, back to the negative terminal of the battery. Let's look at another view and focus on two things: the direction of the flow of current, and therefore the magnetic field that is set up on the conductor itself. So there are two things going on here. The round rings here are the concentric magnetic field lines set up on the conductor as a result of the flow of current, and these interact with the main magnetic field set up from the north pole to the south pole, which are shown as pink arrows. And due to this interaction, the conductor rotates or undergoes a torque inside the magnetic field. So the red arrows here show the direction of the current, as I explained before. This is a close-up view of how the positive side of the battery connects to the commutator A, and how the current flows therefore through the conductor all the way back there and all the way around to the right hand side of the conductor and back to the battery. This is what creates the interaction between the magnetic fields of the conductor and the main magnetic field. Let's look at an animation and it will be more clear. So due to the arrangement of the positive and negative terminal of the battery, and due to the arrangement of the north and south pole, we get an anti-clockwise rotation. The question can be, why is it rotating in an anti-clockwise direction and not in a clockwise direction? To understand that, we must revisit Fleming's left-hand rule and apply it practically in this situation. So Fleming's left-hand rule is shown here. The forefinger points in the direction of the magnetic field, the middle finger in the direction of the current that we are applying to the conductor, and therefore the thumb will show the direction of the force. So in our case, if we remove all the other components, we can see two left hands. The left hand segment of the green conductor has got a thumb pointing downwards, as you can see, due to the direction of the current, which is shown as an orange colored arrow. Therefore, the left hand conductor goes down, and the current that comes back on the other side of the conductor is in line with the middle finger of the Fleming's left hand rule, and therefore the thumb is pointing upwards, which means this conductor will be pushed up. So if we look at an animation now of the current flow and the direction of the motion, you can understand why the rotation is anti-clockwise. It has to be in line with the application of the Fleming's left-hand rule, and that would of course depend on correctly applying it, considering the direction of the main magnetic field and the direction of the current. That's all we need to be careful about. You can also watch the motion of the commutator rings. This is a good place to observe that, and you can see that the orange and pink commutators are split in halves, ensuring that the direction of the current is always pointing as per the Fleming's left-hand rule. If the commutator rings weren't there, the motor would stop rotating. So as the rings pass by and contact the positive side of the brush, the direction of the current is maintained always in a consistent direction, and that ensures the direction of the thumb as per the Fleming's left-hand rule. Now we come to individual positions of the conductor and the commutator ring. This particular image is easy to understand. There is a particular position where the gap in those commutators will be in line with the brushes. We'll talk more about that. If you take an absolute front view, you can see that the brushes, the positive and negative brush, is not in contact with either of the commutator rings. This happens in that absolute vertical position of the green conductor, the vertical plane. Therefore, because there is no current flowing through the conductor, there is no magnetic field set up in the conductor. Therefore, no interaction with the main magnetic field, the pink arrow from north to south pole. Therefore, no force on the conductor. This creates a slowing down of the speed of rotation, but it is maintained by inertia, and practical motors have a lot of commutator segments to give that smooth motion. Now the commutator has rotated by inertia and the brushes are back in place, and the brushes send the current flowing through the conductor. The rings are back in action and the rotation continues. Once again, the brushes come to the point where there is no contact and the same story repeats. So this is the brief description of the working principle of an electric motor. Moment you change the terminals of the battery or you change the north and south pole directions, be sure to apply Fleming's left-hand rule afresh. I hope this video was useful to you. Thanks and have a great day.